In this video, we will see how to derive the optimal solutions to the utility maximizing problem when the utility function is of the quasi-linear form. It's called quasi-linear. As we can see here, u is a function of two goods x and y, and y appears in a nonlinear way. So this is an example of special interest to economists when we might be studying a particular good y, and then x captures all of the goods. So here we have been able to identify and isolate one good y, and then we club everything else as x. So this is a quasi-linear utility function. And then our conditions are the standard budget set, where the price of x times x plus price of y times y equals our income. So to solve this, we'll first set up the Lagrange function, where we again write in the utility function and then we write the constraint, and we include the Lagrange multiplier. So with this setup, the way we proceed is like we've always done, where we'll find the partial derivative of the Lagrange multiplier with respect to x. Now x is just by itself, so the derivative of x with respect to x is 1. Then log y goes away, and then we move on to this third expression, and we see that the derivative of x in this parentheses is just px. So we have minus lambda times px equals 0. Coming to y, the derivative of the partial derivative of log y with respect to y would be 1 over y. This is what we have. And then we have minus lambda times py equals 0. And then the third condition, or the derivative of Lagrange with respect to I, is just the budget set in itself. And we can now work with these conditions. We see that this is a much simpler utility function than, say, the Cobb-Douglas or the CES that we have done, because we can actually start forming solutions even just from here, because the first two equations will give us the value of lambda, and then with that we can get the value of y quite straightforwardly, and then we can plug that into the budget set and then solve. So let's see how we proceed with this. So we can kind of rewrite our first condition to imply that lambda times px equals 1, or lambda is 1 over px. Now we look at the second condition, and the second condition says that 1 over y minus lambda py equals 0, or 1 over y equals lambda over py. And then we can rearrange these and get our y equals 1 over lambda py. Now, what is lambda? Lambda we had already found above, so we can use this value here. Our lambda is 1 over px, so this implies that 1 over lambda is px, because we can just invert or take the reciprocal of this. So we can now plug in our 1 over lambda as px. So essentially what we get is that our y star equals px over py, where we have replaced 1 over lambda with px in the numerator. So notice that our value of y star is now purely a function of the two prices and is independent of income. So this is one way to see that there is no income effect in the Marshallian demand function for good y, which is the quasi-linear function here. So we can use this in our budget set. So let's rewrite the budget set. Our budget set is pxx plus pyy equals I. So we'll just now plug in the value of y star for y. So we get px times x plus py times our px over py, because this is what our value of y is, equals I. And then the y's get cancelled. We can do some simple algebraic manipulation now. We see that we have a pxx plus px equals I. So we can move the px by itself to the right hand side of the equality, and we get pxx equals I minus px. Now this means that now we can just divide our I minus px with px. So our x is I minus px over px. Thus for the quasi-linear function when u is given as x plus log y, x star value is I minus px over px, and our y star value is px over py. And now we can also plug these in our utility function to get the indirect utility function, which is essentially showing us the highest utility this consumer can get if they consume the optimal amounts of x and y given the budget set. So plugging these in, we will get that our x is I minus px over x, and then for y we plug in log of px over py. Now notice that we can now split out our px over py because this expression is in the log form, so we can write this as I minus px over px plus log px minus log py, because py is the numerator, and then applying the rule of logs, that the log of a division is converted into the subtraction of the logs. So our indirect utility function is now given by I minus px over px plus log of px minus log of py. Now we can also transform this, and from this we can get the expenditure function. To get the expenditure function, we will just invert this indirect utility function. We replace our v with u, and we will replace our I with e. Or now notice that we can multiply everything by px. So because we replaced u with v with u, we will get u here. U times px will be px times u. And then we can also multiply our right hand side by px. So from this expression, the px will go away. So we'll just have I minus px. But then we'll multiply px with both log of px minus and minus log of py. So what we essentially get is px times, in parentheses, log of px minus log of py. So just pause there and see that all we have done is we have just replaced our v with u in the first step and then multiplied everything by px. So we've been able to get rid of px from here, and then we have this expression times px. Now the next step will involve rearranging this expression, where we will convert this I into e and then get this by itself. So what will happen is that everything else that we see here will then be moved to the right hand side. Or, if we move this here, then we move this to the left hand side. So essentially we are trying to get I isolated and write I as e. And just to recap, we multiplied the expression with px on both sides, and then we simplified it into px times u. And then our next step will essentially entail getting I by itself. So we are now throwing all of this to the other side to isolate I and then convert that into e. So what we get by rearranging this is that e of, as a function of px, py, and u, is simply our px u, which is over here, and then plus px, so that's what that px is, and then minus px times this. So we have minus px times log of px minus log of py. So this is our expression for the expenditure function. And we can kind of write this in a little cleaner way by taking px as common. Now px appears here, px appears here, and then px appears here. So if we pull out px, we get this u by itself, and then we have minus ln px, but then we have a minus px times a minus, which becomes a plus ln py. So thus the change in sign, because we foiled this expression. And then this plus 1 is just this px by itself. So again, just to convince yourself, multiply px through, and you should get this expression. So we are getting, so all we have done is we have taken px as the common factor. So this, our expenditure function, is simply px times u minus ln px plus ln py plus 1. Now, once we get the expenditure function, we can also get the compensated demand function for y. And to get the compensated demand function, we'll simply differentiate the expenditure function partially with respect to the price of y. Again, we're focusing on good y because that's the good of interest. X is just all of the goods that the consumer is consuming. Our focus is on y. So the compensated demand function is simply the partial of expenditure function with respect to py. And we can then just plug in our actual expression for E here. So this is the partial derivative of our E with respect to py. And now notice what all that's going to happen. Here we have a px times u. This will go away to 0. And we have a px times ln px. That will also go away. Then we'll have a px times plus log py. And now here we have a py. So this will essentially be px divided by py, because the derivative of log py will be 1 over y with respect to y. And then this will again be 0. So if we do this, we can kind of FOIL our px for simplicity. Once we FOIL this, these arguments again become clear. So we have no py here, this goes away. We have no py here, this goes away. We have a py here, so we will be differentiating partially this expression. And then there's no py, so this will go away as well. So what we get then is that our partial is px times 1 over py, or px over py. So in this quasi-linear function, we find this interesting observation that our compensated demand function is actually the same as our Marshallian demand function. And this is a unique property because there is no income effect. So because of no income effect, a compensated demand function and Marshallian demand function are identical.